So, welcome to lecture 12 of this series on several variable introduction to several variable calculus. And in this lecture, our goal is to talk a bit about smooth maps. Yeah, so this is the primary goal of this lecture, to talk about smooth maps, and then I'll try to give a very abstract notion of what a manifold is, because in the previous lecture we had essentially talked about a manifold, but that was a very sort of not much a definite definition. So in this lecture we will try and talk about very briefly. I'll try to keep it as brief as possible, that what a manifold typically is. Fine. But before that, before going into smooth maps, let me quickly give two very important properties of derivatives, which I should have discussed in some previous lecture, but I missed it. So let me just go back to the notions of derivatives once more. So here's a very important property which I am stating as a theorem, that suppose f maps a convex set. So I guess you guys know what a convex set is. So a convex open set E residing in Rn into Rm, f is differentiable in E, and there exists a real number m such that the norm of the derivative is less than or equals to m. So you can think of it this as the operator norm, fine. This happens for all x in E. Then the norm of f of b minus f of a, this is less than or equals to m times norm of b minus a for all a b in E. Okay, now this seems to be quite easily observable, because you can think of it in this way, that if you bring the norm of b minus a to the left hand side, and then you take the limit b goes to a, then you should be readily coming to some point of the derivative. But rather than, let us understand that, because we need to make use of the convexity as well, so it's not that trivial as it seems to be. Proof: so simply fix the coordinates a, b in E. Let gamma t be a line segment joining a and b, and we know that this should be completely inside E, because we have chosen E to be convex, right? So yeah, so let this be for all t in R, and gamma t then is completely inside E, since, sorry, it should be a point, right, since E is convex. Fine. Or rather, I shouldn't write it in this way. Gamma t should be in T for all 0 less than equals to t less than equals to 1, since E is convex, right? The line segment joining A and B. Yeah, fine. Okay, what more can we do? I guess we don't need convexity anymore. Okay, so what we do is that let gt be the function f evaluated at this path. Okay, then by the chain rule, g prime of t should be f prime at gamma t times gamma prime at t, right? So this is just f prime at gamma t, and what is gamma prime of t? It is just b minus a. Fine. Just take the norm on both sides. So this is norm of g prime of t is less than equals to norm of f prime gamma t. This is again the operator norm. You can easily observe that, because these are linear operators. This is b minus a, but then we know that this implies yeah, or rather, let me just immediately add it here, because the f prime is bounded by m. So this is simply this, right? But then observe, but this happens for all t belongs to 0 1, right? So if I just put t equal to 0 and t equal to 1, what should happen, right? Also clearly g at 1 is equals to f at a, right? And yeah, I guess no, g at 0 should be f at a and g at 1 is f at b. Fine, fine. Now you can observe this, that once we define gt to be this, then this is actually a function over r, because I am choosing t from r, right? So I can think of the mean value theorem being applied to r once I think of this in that way. So once I think of the mean value theorem, because g takes in real values, g takes in t is a real number, right? Therefore by the usual MVT in one variable, that is what I specifically mean, in one variable, this g prime t, this can be evaluated to being g at 1 minus g at 0 is less than equals to m times b minus a. Fine. And this implies that, okay, and this implies that f at b minus f at a is less than equals to m times b minus a. This has an immediate corollary. If f prime x is 0 for all x in E, f is constant. Why is it so? Just to this proof, to this previous proof, take m to be 0. Once you take m to be 0, you will get f b equal to f of a for all b not equal to a, and you are good to go. Fine. Yeah. Okay. Yeah, fine. Now let us come back to what we actually initially wanted to talk about in this lecture. Okay. Yeah. So let us straight away go to the definition. So what do I mean by smoothness, right? That is what I mean. So by smoothness, I actually mean that some sort of linear approximation exists as much as we require. Okay. So intuitively, if I speak about, we can linearize it as much as we require. Okay, you can think of it in this way, that smoothness means that a function is said to be smooth in some sense if the approximation, the smooth the linearization of that function can be done as much as we require and can be done in all possible ways. Fine. And that's why we call it to be smooth, that is, there are no, yeah, one more sort of thought, you can think of it in this way, as a smoothness. Like if you recall the one variable calculus, there we had seen that if the graph of a function admits some irregularity, some sharp irregularity at some point, or some sharp kink at some point, then at that point the function cannot be differentiable, because the tangent is no more valid at that point. Fine. For example, the function mod x, if you recall, fx equals to mod x, this was not differentiable at x equal to 0, and in our one variable text it was somewhat told to us, see, we can rigorously prove that it is not differentiable, but seeing the graph at it, we sort of guess that due to this irregularity at that point, at a sharp irregularity, the differentiation or the differentiability does not hold at that point. And this is somewhat you can relate it to the smoothness, that is, if I have a function, so just think of it in one variable way. If I have a function which does not admit any sharp irregularity, any sharp bends or nicks at any point, then it seems to be something which we generally in very literal sense call smooth. And a smooth function, obviously continuous, that is something which we prerequisitely require. So that function which does not appear to have any sharp bends, which deliberately looks to be what we literally call smooth, these functions are differentiable. right? These functions are differentiable, and once you differentiate this function at some point, then at that point we just get a tangent line, right? We get the slope of the tangent line, fine. But then when you differentiate it, you get the slope of the tangent to the tangent line in some sense, or the rate of change of the tangent along the curve, fine. But once the function itself is smooth, you can think of it that you can continue differentiating it as much as you like, as many times as you like, right? So the smoothness in an n variable case is somewhat similar to this. So a map f from U in Rn open to Rm is called smooth if, so in the last lecture we had used a notation, if f is C infinity U, that is f has partial derivatives of all orders. That is, you can talk about 3, 4, 5, 6 and so on and so forth mixed partial derivatives. It has partial derivatives of all orders. And immediately some easy consequence is that since it is infinitely partially differentiable, each partial derivative is continuous. So each mixed partial derivative is continuous. So the Clairaut's theorem holds here on its own. That is, del 2f by del xi del xj is same as del 2f by del xj del xi, sort of things like that. So here we need not be concerned about whether the order of the mixed partial derivatives can be interchanged or not. It is readily available because all the mixed partial derivatives exist, and once you need to partially differentiate each partial derivative, that needs to be deliberately continuous, right? Fine. Now the thing is that obviously we cannot talk about, as we have seen continuously in the several variable case, that it is not possible to talk about these the properties of the derivatives in general over the whole space, right? This is something which we are readily seeing over a long time, that whenever we want to talk about something, we prefer to talk about it in a local sense, that what happens if I take a small part and talk about that part itself, not the whole space, okay? Now the thing is that we also have seen deliberately from the previous lecture that whenever we want to talk about differentiability over some space, we have deliberately taken that space to be open, because whenever we talk about differentiation, we are deliberately talking about limits, and in an open set, each of these interior points, I mean the open sets, every point in an open set are such points that there exists some neighborhood such that that neighborhood is completely contained inside E. So whenever we talk about open sets and each of these points, it's actually required those points to be limit points whenever we are talking about derivatives, and this makes it easy to talk about open sets. So you require open sets whenever you, or at least interior points whenever you talk about derivatives, fine. Okay, so what if we are not given an open set, rather an arbitrary space, okay? So suppose you have a map, let it be a map from X to Rn, fine, okay, yeah. So let it be a point from X to Rn, then this is called smooth, See, let me just talk about something more before moving on to here. A more precise notion of why we require open sets is very easy. See, we are here at every point we are talking about the standard topology. Do not think about an arbitrary. If you have studied topological space, there are multiple topologies which you can define, but basically all the topologies are equivalent over finite dimensional spaces. That is something which we know, but rather whatever we are talking about are standard topologies, the standard Euclidean topologies. Now suppose you have an open set and this is a point X, and you take you have some ball which is completely contained inside. Now you can obviously observe that if you reduce the radius of the ball, it will still be contained inside, and if you increase the radius of the ball, if you keep increasing the radius of the ball, the ball will, it might not be completely inside this region, but it will intersect this region, and it will intersect this region at other points except the center x. You are getting the notion of a limit point here, right? Yeah, that is why we require open sets. Fine. Okay. So yeah, let's get back to what we are trying to discuss. So suppose f is a map from x to Rm, let's say, where x is some arbitrary set in Rn. Okay, we are not assuming it to be open, so it's some arbitrary set in Rn. Then f is called smooth. So we want to talk about the derivative, but we cannot talk about it immediately because x is not given to be open. So what we do is that we localize the definition. So when f is called smooth, if what should I say, that if at each x in X there exists an open set U in Rn containing X and a smooth map F from U to Rm such that F exactly equals F, small f, on U intersection X. Fine. So what are we actually doing here? Let's observe. Suppose this is my X, not necessarily open. I have a function from here to Rm by small f. We say that small f is smooth if at every point X we can get hold of an open set U in Rn, fine, such that there exists a map capital F from U to Rm, and U is open, we can talk about differentiability. So f is smooth, this is smooth, and capital F and small f are same in this intersection. Fine. This is a notion of what we call a local extension. This is what we call a local extension, or a more lame term should be localization. Sorry, localization of maps. Fine. Yeah. Okay. Fine. You can also think of this to be the subspace topology of X, right? If you study topology, you can easily relate it to be the subspace topology, because we know that in a subspace topology, if X is some arbitrary subset of a topological space, then the open sets in X are basically the sets of the form U intersection the higher space where U are the U intersection X where U is an open set in the higher space. Right, this is the definition of a subspace topology. You can see that we can relate this to a subspace topology, because U intersection X will come out to be the an open set in the subspace topology of X, where U is an open set in Rn, because Rn is the higher space. Fine. Okay. So smoothness is typically a local property. Okay. Now we had studied something called a homeomorphism between two topological spaces, right? So now let X and Y be two Euclidean spaces, whatever Euclidean spaces you think of. So let X and Y be two Euclidean spaces, and let F be a map from X to Y. Okay. Then recall that F is called a homeomorphism. F is called a homeomorphism if F is continuous, F is bijective, and F inverse is continuous as well. F inverse is continuous as well. And in this case, whenever two spaces are homeomorphic, we say that they are topologically equivalent, right? They are topologically equivalent. But whenever we have two differentiable spaces, in some sense, what do I mean by differentiable spaces? That suppose I have a function over to between two Euclidean spaces which are differentiable. think of it locally, whatever you might feel, you can think of it to be differentiable in the whole space, because if you talk about them being topological, then the whole spaces are open by definition of a topology. So what do I want to do is that I need to get hold of a stronger notion than homeomorphism whenever we talk about differentiability. So here comes the notion of what we call a diffeomorphism. So f from x to y, x and y are still Euclidean spaces, is called a diffeomorphism, if f is differentiable, or rather not only differentiable, f is smooth, that is all orders of partial derivatives exist, f is smooth, f is bijective, and f inverse from y to x is also smooth, that is f is a C infinity function, it's bijective, and its inverse is also a C infinity function. In that case we say that x and y are diffeomorphic. Okay, so I guess this is a, yeah, so in this way we write diffeomorphic, or rather we will use this symbol. So x and y are diffeomorphic, and it's sort of a stronger notion than homeomorphism, because once you have differentiable functions, they are they are already continuous. So once you say that a function is C infinity, it's already continuous, and the inverse map is C infinity, so again the inverse map is already continuous, so they are already homeomorphisms. But these are something stronger, we need the differentiability as well, and here we have what we call a diffeomorphism. Fine. And again, two diffeomorphic sets are intrinsically equivalent. Okay, they are basically two copies of a single space, a single abstract space in different situations. Fine. So let us give some examples, and the examples are some sort of interesting because we will give examples by figures. Fine. See, if I talk about a cube, see, I cannot explain this completely at this point because we don't yet have the necessary tools yet. But if I have a cube and I talk about a torus, okay, I talk about a torus and a cube, then these two are not diffeomorphic. These two are not diffeomorphic. Okay. And you can think of it due to existence of a genus here and no genus here. So there is a difference in the topological structures of both of them locally, some sort of locally or globally, whatever you think of. Rather, it's a global distinction. Yeah, but these two shapes are not diffeomorphic. While if you talk about something, sort of a thing like that. Okay, let me draw it a bit smooth. Something sort of a thing like that, and you think of something like an octopus, then these two are diffeomorphic. Fine, these two are diffeomorphic. For example, if you talk of a triangle and sort of 8, these two are not diffeomorphic. These two are not diffeomorphic. You can think of it as the existence of this intersection here. Okay, this will actually give you a difference in the in the structure of the local spaces. Okay, these are rather examples coming out from rigorous discussions on manifolds, but still it's quite interesting to talk about these spaces, and so I'm keeping it up. While if I take a smoother circle, a smoother triangle, and I talk about a space which is not intersecting but tangled together, so sort of a thing like this. Yeah, so fine. Yeah, fine. Yeah. These two are diffeomorphic. Fine. Okay. Yeah. Okay. So these things are quite interesting to see, but rather mathematically we have not yet developed the tools to talk about them being diffeomorphic. But these are some sort of abstract spaces. You can see. These are some sort of abstract spaces. Okay, and each of these abstract spaces holds some resemblance to our standard Euclidean spaces. Okay, for example, if you take up this space and if you choose some point and a neighborhood around that point, then that point will sorry yeah, so if you choose some point and you take a neighborhood around that point, then that point will resemble to a sphere in the standard Euclidean space, and the same will happen here as well. If you choose a small enough neighborhood, it will resemble a sphere. Okay, but here it won't be the case. Here it won't be the case at every point. Okay, there are some things called structures with structures and structures with boundaries. There are some differences appearing, but we are not going to discuss that in this lecture, but rather there are more rigorous things in that form. Similarly, if you talk about the this smooth triangle, then at every point, if you draw a neighborhood, it will some sort of resemble a circle. Fine, this is typically not, the interior is not present here, the interiors are present here. Okay, so I need to draw it like this, the interiors are present here. Okay, these are not interiors, these are just the boundaries, sort of the boundaries itself. Fine. Yeah, fine. Here also in the torus we have the interior. Okay, fine. Okay, fine. See, this smooth triangle, this will actually refer to a circle in some sense, and this entangled version will also, okay, in some sense, while these here it won't be happening due to the possibility of this intersection and these sharp bends. Okay. Yeah, okay, let's end this part here. Rather, let me go into the thing which I actually wanted to introduce in this lecture, which is the notion of a very abstract notion of a manifold. Okay, let X be in Rn, and or rather then X is called a manifold, a k rather a k dimensional manifold if it is locally diffeomorphic to Rk. Fine. What do I mean by this? Suppose this is my X and it resides in some higher space, it resides in some higher space Rn. Okay, okay, let me draw it in the next page itself. Okay, wait a minute. Yeah, fine. Okay, so suppose this is my X, this is my X. What I'm trying to say is that if I choose any point out from X, okay, then there exists some open neighborhood V around X such that it is diffeomorphic. There exists a function phi or a function f which is diffeomorphic to some open set U. This is Rk and this is open. Okay, so they are intrinsically equivalent, they are topologically as well as differentiably equivalent to some open set in Rk locally given. So in a more simpler sense, what I am trying to say is that if you take X, you choose any arbitrary point from X, you pictorize the neighborhood of X, then this neighborhood will seem to be exactly open set in the k dimensional space. Fine, fine. For example, if you go back here, where was this? Yeah, so every neighborhood around each of the points in this space will look like a sphere which are open sets in R3. Getting my point? And so is here. Got it? So these two spaces are locally diffeomorphic. So a manifold is basically, we can actually talk about manifolds in general, that is we do not require X to be residing in some ambient Euclidean space, but we can actually talk about what we call a generalized surface. We have not yet discussed those things, but a generalized surface you can think of as a Hausdorff second countable and I guess local Euclidean topological space is called a manifold typically. So if I choose a space which resembles the properties of a metric space or a Euclidean space in some sense, that is Hausdorff and its second countable, then and furthermore, if I have that around every point in that space we have a neighborhood which is diffeomorphic to neighborhoods in some Rk, then that space is called locally Euclidean in dimension k and it becomes a manifold. Fine. So manifolds are basically surfaces which locally resemble an open set in some Euclidean space. Fine. Got it? Okay. Yeah. So for example, if I talk about a snail, let's say, then any neighborhood, if I choose any point and I choose a neighborhood of that point, then it will resemble the closed interval in R. So you can think of that this space to be a one dimensional manifold. Fine. Clear? We need to there are some more things here to talk about. For example, we can't associate this exact boundary to this space and so on and so forth, but rather this example is enough to give you a visual representation of what a manifold looks like. Fine. Okay. Yeah, in fact it won't cause a difficulty, because if you choose a point here and a neighborhood will be some sort of this, it will still represent a a closed interval or a line segment in R. Fine. Okay. Yeah. So once we have a diffeomorphism of this set of this sense, so a diffeomorphism phi from U to V is called, so V was a neighborhood around a point in the space X, and U is the open set which is diffeomorphic to that neighborhood in Rk. So is called a parameterization of V, and phi inverse from V to U is called a coordinate system of V, because the reason that this phi inverse, since it resides in Rk, it has some coordinate structure. In that case phi inverse can be written as x1 till xk, and it's a n variable function. So with n variable differentiable functions, k variable differentiable functions, where each xi are smooth functions on V, which we call the coordinate functions. Okay, which we call the coordinate functions. Fine. Okay. Yeah. So this is so let this lecture be up till this much, because it's already past 30 minutes. In the next lecture, we will give a beautiful example of a manifold, and I will try to complete this series in the next lecture itself. But if not, then we will come up with max to max one more lecture regarding some other topic. Okay, some other important topic. Okay. So meet you guys in the next lecture.